So suppose we'd like to use the definition of the derivative to find d dx of the square root of x. Before we do anything, before we actually compute the derivative, we need to recall a couple of things. One of them is, what is the definition of the derivative? This is particularly important for those of you who have had calculus before and want to jump right into using formulas. So we need to think about derivatives in terms of their definitions right now. And the second thing we need to tackle is this notation. What is d dx of a function? So let's go ahead and handle those before we do any work. So let's recall. First thing being this notation. So this d dx of just a function in general. Another way that we can write this is df dx. This makes us think that the derivative is a change in y over a change in x, or a slope. Another way we can write this is d acting on f of x. And this makes us remember that the derivative is an operator acting on a function. And the last and probably most common way to see this written out is f prime of x. And this reminds us that the derivative is just a function. So these are all, different ways that we denote derivative, and they're all equally valid. The second thing that we need to remember is this definition. So d dx of f of x, how do we define it? Well, derivatives are defined in terms of a limit, right? It's a limit as h gets small of a difference quotient. That difference quotient being f of x plus h minus f of x all over h. And this is the definition that we're referring to. So now that we have those definitions out of the way, we're ready to tackle the problem that we have, and that is looking at trying to find d dx of the square root of x. So our f of x is square root x, and let's apply this definition that we have to it. So we were looking for d dx of root x. By definition, this is a limit as h goes to 0 of this difference quotient right here, right? So for our function, we're going to have the square root of x plus h minus the square root of x all over h. Now the first thing to do when evaluating any limit is to see if this limit or if this function on the inside is defined when h is 0, and ours is not. So this tells us that we need to do some more work. We need to do some algebraic trickery on this function right here in order to obtain another function, which we will take a limit of. But this function over here, what's important about it is that it's defined at h equals 0. So that's what's important about it. And you might be wondering, what in the world are we going to do with this function in order to get that kind of quality out of it? Well, if you have no idea, one common trick that is useful whenever you see a difference of square roots is to rationalize. So let's go ahead and do that. So we're going to take a limit as h approaches 0, and I'm just going to rewrite our expression as it is before we rationalize. So we have this times, now remember we're going to multiply by the conjugate of the top, so we're going to multiply by the square root of x plus h plus the square root of x all over, well, the same thing, right? And notice that this quantity that we've multiplied by is essentially 1. Not essentially 1, it is 1. We've multiplied by 1, so we haven't changed the expression, and this is something that's totally allowed. Now, the whole point of multiplying by a conjugate is that this numerator now is going to simplify to something that does not involve square roots. So let's look at what that is going to be. So we still have a limit as h approaches 0 out here, and I want you to notice that I continue to write this not because I'm being picky, but because that's how we're able to say that we have equalities, right? It wouldn't be an equality if I dropped the limit off. So when I multiply these factors together, I'm going to get x plus h from the product of this term and this term. I'm going to get minus x from the product of this term and this term, and then the cross products will cancel. I've designed it to be that way. On the bottom, I have h times the quantity square root of x plus h plus square root of x. And now I stand back and look at what will cancel. Notice that this x and negative x cancel. So on the next line I have the limit as h goes to 0 of what? Well, on the numerator I just have h. On the denominator I have the same thing, h times the quantity root x plus h plus root x. And then what's really nice now is that these h's will cancel, right? So this is the limit as h goes to 0 of 1 over root x plus h plus root x. And now this function is now defined. Let me put my parentheses in here. That function is defined at h equals 0, which is the quality I wanted to see, right? So that tells me that I'm now able to evaluate this limit right here. And when I plug in h equals 0, notice that I get 1 over root x plus root x, which is 1 over 2 root x, which is precisely what my derivative is. 1 over 2 root x, or if you will, 1 over 2 times x to the negative 1/2 power. And this is the derivative of the square root of x.